Hi, I'm Drake Ealer, and I'm a sophomore in aerospace engineering, and I'm one of the team leads for our Argonia Cup team.
My name is Chris Whitlock. I am a second-year master's student at the University of Kansas in the aerospace department. I am the team lead of payload and propulsion.
Hello, my name is Simon Clark. I am a sophomore, and I am the vice president of the Jayhawk high-powered rocketry team, and I am one of the Argonia Cup co-leads.
All right, my name is Tyler Ackerley. I'm a junior in aerospace engineering, and I work on the structure sub-team.
Hi, I'm Benjamin Smith. I'm a freshman, and I'm part of the design team.
Hi, my name is Zach Norsby. I'm a junior, and I'm part of the structure sub-team.
There's 2 or 3 back here.
Hi, I'm Raymond Singh, and I'm a sophomore. For our Argonia rocket, I worked on optimizing it.
Hi, my name is Jarrell Miller. I'm a third-year grad student, and I'm in charge of the structures and structural design, so I lead that team.
I'm Connor Fortin. I'm a freshman, and I'm on the electronics sub-team.
My name is Connor Mispegel. I'm a freshman, and I'm on the payload sub-team.
Hello, my name is Simon Clark, and I am one of the Argonia Cup co-leads. So I'm here to talk a little bit about our actual rocket itself. So our method was we really wanted to use carbon fiber because of its lightweight, and it has a lot of strength. And so our strategy to develop that was first we printed these molds, 3D printed, and then we just did a simple layup with carbon fiber, wrapped it around this inner body tube, which has a diameter of 4 inches and a length of 36 inches. And then we essentially just vacuum packed it, and then we left a little seam just because, so the rest of it isn't really wrinkly. So we got this, which is our really strong, really lightweight sustainer section. No, it's not, it's booster section. And so this is part of our sustainer section. This is actually our payload section, well, a mock-up of it. And so this is essentially just an increase from 4 inches to 5 inches of diameter, and this is where all of our payload golf balls will be held as we bring it to altitude. This will also be made of carbon fiber. And then finally, I'd like to talk a little bit about our fins. So these are also made out of carbon fiber just for its lightweight and strength. And so again, we just did a layup with some foam core in the middle, and it's not a flat plate because we wanted to get that symmetry on both sides. But yeah, so that's a little bit about the actual construction of our rocket.
Hello, I'm Benjamin Smith. I'm part of the design team for Argonia Cup with high-powered rocketry. We decided to use OpenRocket as the software that we're using to design the rocket itself. We chose OpenRocket because of the long history we have using OpenRocket and the swiftness that we can get a design buffed out to start making prototypes. We chose to do a 4-inch body as for the boosters, and then a 5-inch diameter payload section. We chose the 5-inch compared to a 4-inch or 3-inch or whatever to have more golf balls inside the payload section, and we are shooting for about 2.5 miles high with 2 motors and carbon fiber built.
All right, hi guys, my name is Jarrell Miller, and I primarily help with the structure and overall body design. So for the rocket, we transitioned because we did the diameter of multiple golf balls, and so we optimized for the diameter of the golf balls, and then we also optimized for the minimum ply count of carbon fiber based on the load the rocket will see.
Okay. Hi, I'm Drake, and I'll be talking about the overall team structure for our Argonia team. So our entire team is part of the club called Jayhawk High-Power Rocketry, and within that, all the competition leads were decided within this club prior to having our first team meeting. And the decision of that was discussed among the club executives based on our interest in leading the club or team, and then along with having the necessary experience and longevity within high-power rocketry and the club itself. So as of the first meeting, the team brainstormed design decisions and everything. That was all before just separating into sub-teams. And then following that meeting, sub-teams were basically decided based upon the needed design components within the rocket. And so these sub-teams included the body, payload, propulsion, and avionics team. And then following the creation of those sub-teams, leads of each sub-team were decided based on the strength of each member, and then the other members of the team were basically divided between these sub-teams where it was necessary. And then for the entire project, the team leads created an overarching, basically, schedule for the entire project, and through that helped ensure that the team was able to stay on schedule, and then also guided tasks needed each week, and then also the priority of the design decisions. And then for each subsequent meeting, the team leads created basically deliverables to be done during each meeting, as well as deliverables to be done for the next meeting as well. And then during and after those meetings, this entire team had basically discussions about the design decisions themselves.
Hello, my name is Kyron, and I work on the electronics for the rocket. As of today, we don't have any of the electronics for the rocket due to supply issues. But while we don't have the official system in our hands today, we do have a good idea of what the system will look like. So with the electronics, we aim to have the system as simple as possible. To do this, we utilize the electronics we used previously by our team members. With our electronics, we needed to detect launch, booster motor burnout, and apogee. It also needed to separate the booster motors, it needed to separate the booster stage, the sustainer stage, start the sustainer motor, and deploy the sustainer parachute at apogee. We also wanted redundancy within our altimeter system just in case we had launch issues or logic issues with one of the altimeters. We also needed to have a solution to track the booster and sustainer stages. We sourced our altimeter, receiver, and tracker from 8-timer Rocketry. Our members have used both the 8-timer altimeter tracker before, and they worked well enough for us to use in this project. We are getting LiPo batteries from Hobby Keen, and we also got deployment materials from Chris's Rocketry supply and Apogee components, and various other components were sourced from local hardware stores as well. As far as the tracker, we are using an egg finder mini. This allowed for a smaller footprint, allowed for more electronics and more payload to be used within the rocket. The egg finder mini also sends coordinates of the booster and sustainer stages to a handheld LCD receiver for us to easily recover each stage. The flight computer or altimeter for our rocket is the 8-timer Proton. The Proton was selected because of its robust sensor and logic suite, and also its many deployment channels. Because of this, the Proton is able to satisfy our altimeter needs. As far as the Proton, it has a barometer and accelerometer sensor. I said that wrong. The Proton has a barometer and accelerometer sensor for velocity and tilt control. The Proton has barometer and accelerometer sensors, which allow for detection of velocity and tilt angle. With these sensors, it's able to house deployment and air start logic using lockouts such as velocity and time or altitude and time controls. As far as wiring, the Proton is housed within an eBay and then wired to the deployment sustainer motor and the parachute for the sustainer section. This was done to simplify the electronic integration within the rocket and the wiring system as a whole. As far as ejection charges, we'll use black powder ignited by E-matches, and also shear pins will hold each of the stages together during flights. Finally, the jelly logic chute release is utilized to delay parachute deployment for the booster and sustainer stages.
My name is Chris Whitlock. I am the flyer of record and one of the team leads for our Jayhawk high-powered Argonia Cup competition team. My job primarily was working on the optimization problem of figuring out what's going to be the best combination of rocket motors if we're trying to maximize altitude for any of these possible flight case scenarios. That started by taking existing textbooks like the Sutton book on rocket propulsion and putting that into code like on MATLAB, and trying to get a preliminary estimate for the kind of range given the maximum amount of impulse we're allowed to use. Then using a combination of OpenRocket and the official certification list of motors to be able to calculate things like specific impulse and other performance metrics, to be able to then start organizing and creating a list that's probably around like 100 plus motor combinations long, to figure out in then OpenRocket simulation terms which one would have the highest altitude, starting with what would be the heaviest version of a rocket, loaded as much as we can with golf balls, and then carrying over those same simulations with the least amount of weight in terms of ballast, what those two performance characteristics would be. And the end result was the first and second stage motor being the Cicerone L1395 for the first stage, representing about 95% of the initial impulse. And then the second stage being the Cicerone H118, representing around like 5% of this total impulse. Both of those being reloadable motors, sitting in comfortably, whether fully loaded or whether minimum dry mass. So minimum dry mass, maximum dry mass, we're talking altitude in theory of 12,000 to 13,000 feet, as opposed to the rest of the field, which ranged from 5,000 to 10,000 feet.